Thank you very much for the introductions, and good morning, everybody. As mentioned, the title of the presentation today is Critical Role of the Accessible Data, BIM-based Automated Rule Checking Systems. And the outline, I will just go through very quickly, introductions about what we are trying to do. And briefly, I will also go through about current research in the automated BIM-based rule checking. And then I will go into the kind of the heart of the paper about missing piece of the rule checking systems, which is the data. And then follow with introductions of what we have done in terms of getting that solved for the accessible data. And I will go through also a little bit about implementations of it and some examples that we can do with it before I close with the conclusion. So before I get into the topic, I just review a little bit about the objectives. We have been dealing with rule checking systems. I personally have been dealing with it since 2001. That's 16 years. We always have an issue about where to get the data, how to get the data, and how easy it is to get the data. And the topic that you will hear today is part of my thesis. Not all of them, it's a part of them, or a big part of them. And that the whole research is about the rule checking system. And also we deal with how to work with complexity of IFC schema. And another thing that is important and very often overlooked is to integrate not only that the information about the objects and the properties, but also with the geometry and the spatial relationships. So just as an introduction, research into rule checking systems have gone a long way. It started in about 60s when Francis he introduced a decision table. That's in 1966. But a lot more real activities in terms of developing the systems probably started in the 90s. So in 1995, the Singapore government sponsored pretty big projects trying to do that with a BP expert, largely based on 2D. Didn't really work well. It was reset in 2001 or late 2000 with Connect E-Plan Check systems. This is multi-million projects, so I highlighted with different color. Then since then, we see kind of a few other things going on. Solibri started in around the same time, and then we have other research projects in Australia, Design Check. In the US, we have the Smart Codes or Firetech. Then I think probably the recent big attempts, significant attempts, is done in Korea with KBIM. We had a special track for code compliance checking in CIB W78 conferences 2 years ago in Eindhoven. End of last year, Building Smart regulatory room had a small project trying to identify a potential commercial applications for building code checking systems. When I started my PhD research in 2013, the starting point that I tried to do is that we know the research into that systems have been going on for a long time, but we have seen only a small progress. We haven't seen significant progress. So the first thing that we try to do is to identify what exactly, or why is it so complex. We came up with this paper published in 2015 to classify what kind of complexity that we have to deal with in terms of implementations of the systems. So we come up with the 4 classes of the systems or the complexities. The first one deals with explicit data. We focus on IFC, which is anything that you can find in the model, IFC model. The objects, the relationships, the properties, attributes, and so on. But then that only covers a certain scope of problems. We have other scopes that gets more complex in terms of implementation. The classifications number 2 say that it will include additional semantic that you have to derive from the basic data. Classification number 3 basically add more complexity. It has to do with solid modeler and maybe graph. And classification 4 is a little bit more advanced than that by having a knowledge base. Instead of just checking passively, now knowledge base should be able to kind of actively suggest what should be done. This is the first attempt that we try to classify, and we realize when we look at it, it's really dealing with data. So the complexity really comes with data. After the special track for the code compliance in the conference 2 years ago, it was followed with special issues in ITCon journal, and in the editorial we actually put this diagram. This is another attempt to look at or to divide the scopes of what research have been done in terms of rule checking systems by classifying them into what areas of problem domains that is being solved. And this kind of the rough ideas that we look at from the left side is the rules, and there's a research to basically how to transform that rules into computable forms. And the second box in there is what form is that. And the third box is related to it as well, is usually the execution environment. So you have the computable forms, you have a system to run it, and that depends on the data. So on the right hand side you see the data. Some of the system will work directly with IFC models. Some transform that models into some other forms or enrich that forms with some other representation. And so this research focused on that area, which is the data. Why is it important? Because when we look at IFC is designed for data exchange. It's very highly structured, very good in terms of getting the information, less ambiguity in the sense that you know what you get. But as a result, it's actually pretty difficult to get to query information. So this is just an example. If you want to find doors on external walls that have fire rating of certain values on the ground floor, how are you going to do that? So if I give you a model, right, it can be Rabbit model, can be IFC model, how are you going to get that information right now? I've been working with several systems, Rabbit and all these things. I find that it's not straightforward. It's not easy to do it. Find all variable air volume boxes, for example, certain types of certain manufacturers in a special office unit. How are you going to do that? Find all external walls with unprotected openings. So things like that becomes very difficult. And then on top of that, if we have to deal with the geometry, we have to deal with spatial relations, it's even more complex. It's not easy for you to do any query with that. Some people put an idea saying that, well, we can pre-compute those. There's a limit to how much that we can pre-compute because there are some relationship that is not predetermined or cannot be practically predetermined until you actually do something else. So this is just one example. There are many other examples. We cannot get kind of a better one. This is just talking about path, or egress path. The egress path says that you cannot pass through a certain spaces unless you have other potential, right? So 50% of it should not pass, but 50% of it can pass. So that kind of things you cannot pre-compute and then say, okay, these are the possible paths, because then you have to have some logic to determine them. So what are the typical approaches today? If you look at what have been done and what is available today, there are several ways of approaching the data. One is to use a native IFC or Express Data Store like EDM server or even BIM server, I think it's just you see the IFC data, and you have to look at, or you have to develop your own way to query the data. Some stay away with a complex issue, let's say the geometry, you stay away from it. The product, the company I work for, BIMRL, for example, is falls right now into that category. Only deals with objects and properties. Or implement limited support of specific or pre-built logic, like what you will find in Solidly. Or provide APIs, right? That what we tried with Phonics, which is used in cognitive plan check system, but it's very heavy and very expensive to do it. Some stay with native, like Revit Autodesk Model Checker. It's limited to only Revit. So what we try to do really is to look at, okay, is there any way to really help us to be able to query the data in a simple and straightforward, or at least familiar way to do it. All right. That, as I mentioned, includes geometry and spatial. So two major concepts that is involved in it. The first one is simplifying the data into, so we transform the IFC, the complex IFC model, into something simpler. And then we introduce the geometry. The tricky part really when we deal with geometry is how are you querying the geometry. It's always difficult because geometry itself is complex. So what we try to do here is to use multiple representations. It's kind of making the geometry inside out. Right? You will see that later a little bit more. We implemented using RDBMS system. We also try others, but so far the main one is on the RDBMS systems because we do not want to reinvent the wheel. I mean, we have nice SQL statements, a lot of optimizations done in Oracle RDBMS. We want to use that. So the first concept, the major concept I mentioned is a simplified schema. And you will see this, it's a bit too small for you to see, but basically what we try to do is that we simplify the IFC model into this set of 20 tables, just 20 tables. The concept we use is trying to make use of geospatial support for 2D and 3D, limited 3D model. We use RDBMS. We use the data warehouse approach to something called star schema. So we have one kind of central tables, and then we have all the surrounding tables there. Basically allowing standard query language to be done, and most of the information is just one step away from it. Make it simpler. The second major concept is multiple representation of geometry. So what I mean is that here, the original one that we deal with for my research, I take a triangulated data, because that's the easiest one to get and kind of more common, not specific to really IFC. It can also be from any other sources. And we keep polyhedron geometry. This is the one that we can actually store in Oracle Spatial. But also then we enhance that data into the boundary representations with the planar faces. So we get back the simplified planar faces, convex and concave faces with holes. And then we also do other things here with octave decompositions for approximations of shapes, and also act as spatial index. And we have projected oriented bounding blocks and axis aligned bounding blocks. Those informations are available so they can be queried according to the need. Sometimes we need only just bounding box is sufficient, that's the fastest. We can also sometimes need projected oriented bounding box and so on. So what we try to do with that is to come up with something like this. So let's say I want to search that data, specific outlet terminals or end projection screens inside a space that is numbered 106, for example. Why we need to use spatial index is because model sometimes comes from different sources, right? So the space comes from architecture models, and then you have the, say, outlet terminals from something else. And even if it's modeled within the same model, sometimes specific things like outlets is not inside the space because part of it is outside the space. It's part of it inside the wall, so it's not completely inside the space, and therefore will not be inside the space. So you need a special index to do that. This is an example query that you can get with the systems that we are trying to build. It's pretty simple in SQL. And this is an example result that you get. And I will give you a little bit more examples later on. And before we get into that, the introductions about the implementations. So as I mentioned, the architecture of system is this, and this is part of my PhD topic, so the research. There are two major parts of it. One is about the rule language, and this is not the scope of these presentations, but the second one is the part of these presentations, which is how we actually extract, transform, and load IFC data into the simplified schema. This is the process that happens. And we get the IFC files into, we use XBIM to read that, and then create the tables for it, set of tables, so I mentioned 20 tables, process the IFC elements, we get the geometry, the polyhedron, and then process the properties and relationships. So up to here, this is all explicit data. And then we do extra computations here. This is the multiple representations computations. It's actually consists of 4 steps. One is to mention create the boundary faces, create octree indexes, compute the axis aligned bounding box, compute the oriented bounding box. We also took extra efforts here to enhance the space boundary, because sometimes data is not complete. You may have a space boundary on the horizontals, you don't have a vertical. So this is the step where we use the result of these computations to enhance the space boundary. And then we also have circulation graph added to the system. I bring you a few examples here. The first example is very simple examples to validate the omni-class code is correct. So how do you do that? It's very simple. But the idea is really you can do a lot of queries just using SQL statements. In this case, we use regular expressions that is provided by Oracle to check whether the formats of the omni-class code is correct. Right, this is an example. This is not correct because there's a letter here, so it's supposed to be 2 numbers. And then a little bit more interesting example is that we want to query the model. We look for spaces that may have a problem in terms of either modeling error or just simply export errors where space is inaccessible. The idea about accessibility of the space, it has to be accessible by a door, by just an opening, or by another space directly connected to it. So this is an example of a query, simply just a SQL statement. Another example that I would like to spend a little longer time is a complex. This is complex rules. One of the rules that we have in Singapore here is to check whether there's any sanitary systems on top of, say, a potable water tank, drinkable water, or a switching device or transformer. For 2 reasons. One is potential hazard for fire if there's a leakage, drip, or it drips and contaminates the water. Yes, we had an issue one time in Singapore. One of the older buildings had that problem that people get poisoned, and hospitalized because of that. So how to do that? It's not that straightforward, to be honest. It has to go through several steps. In this case, there are 3 queries. The first query is getting the information about the objects of interest. So in this case, there are 3 types of object of interest: the switching device, transformer type, and tank type that has a specific properties of potable, which is drinkable. And then it actually collects the information from the oriented bounding box in the top face of it. So what we are interested is to look for the oriented bounding box of those objects. And then we only want to get the top face. For the reasons that we get the top face, we make an extrusion, and then we can then later on perform the spatial operations, right? The second relatively independent query is to collect all the systems, the sanitary systems, right here. And then the third step to it is to query, so the picture earlier, that is a box that is an extrusion. So based on that box, we can do a special operations to see whether it intersects with any of the objects that belongs to the query, second query. Right. So by doing that, then you can actually get the outcome whether there is anything on top of those objects of interest. So again, if you see all these 3 queries are all based on the SQL statements using the simplified schema that we introduced. Okay, we have to repeat that for every object because those objects of interest are independent. Now you see that it's a little bit more complicated because you have to do several queries. That comes my other parts of the research. There's a rule checking language that actually kind of package everything together into nice things that you don't have to do. You don't have to worry about multiple steps, and it involves the creations of the temporary geometry, for example, to be able to do that intersections that I mentioned. So details can be found in the paper. So one paper about multiple representations already published online in automation and constructions. The other one is still kind of under review for a very long time. And another good news that I have is that I have made the entire extract, transform, load software open source. So anyone who is interested to work with it, to play around with it, you can get it from there. And so the conclusions. Accessible data is important, and the efficient access to data is critical if you want to do automated rule checking systems successfully. What we think is that separation of data and the logic is also important. In this case, we use RDBMS, allowing us to do optimizations of the data, doing indexing, all those things separate from the logic. Integrations of the geometry and spatial is very, very critical. A lot of times kind of doesn't receive due attention. A lot of research done on how to make a computable form of rules, but very little done on the area of data. We try to implement that simplified schema into other things. You know, today we all talk about the sexy things, NoSQL things, and we actually try to do it on the multi-mode NoSQL using OrientDB or RDB. It shows a little success. There's some things easier to be done, but there are a lot more things to do. Performance is still an issue with those systems. So with that, thank you very much.
Thank you. Do you have any questions?